What if everything you thought you knew about time was only half the story? Picture this: somewhere out in the vast, uncharted depths of the cosmos, time might not tick the way it does here on Earth. A single second for us could stretch into centuries elsewhere, or perhaps vanish in the blink of an eye. This isn't just a wild thought experiment. It's a real possibility that physicists and cosmologists are grappling with right now. The idea that time flows differently in other parts of the universe isn't just science fiction. It's a theory rooted in the very fabric of reality, one that could upend our understanding of existence itself. Think about the last time you lost track of time, maybe lost in a great conversation or staring at the stars on a clear night. Now imagine that feeling isn't just perception, but a fundamental truth of the cosmos. Einstein's theory of relativity already showed us that time isn't as fixed as it seems. Gravity and motion can warp it, bending the seconds like a cosmic rubber sheet. But what if those distortions aren't just local quirks? What if the universe is a patchwork of timelines, each region ticking to its own rhythm? From the supermassive black holes warping spacetime to the mysterious voids where time might slow to a crawl, the implications are staggering. This is where the real adventure begins. Over the next few minutes, we're going to unravel some of the most provocative theories in modern physics. Ideas that sound like they're straight out of a blockbuster movie but are backed by cutting-edge science. Could entire galaxies age at different rates? Might there be places where time itself is frozen or even flows backward? We'll dive into the evidence, the debates, and the mind-bending possibilities that could redefine not just how we see the universe, but our place within it. So get ready, because by the end of this journey, you'll never look at a clock the same way again. Time is the silent river we all float on, yet no one truly understands its currents. For centuries, thinkers have wrestled with its nature. Is time a real, tangible thing, or just a trick of perception? Sir Isaac Newton saw time as absolute, an unchanging backdrop against which the universe played out, like a cosmic metronome ticking steadily no matter where you were. But then came Einstein, who turned that idea on its head. His theory of relativity revealed that time isn't rigid. It bends, stretches, and even slows down depending on where you are and how fast you're moving. Picture two astronauts, one orbiting a black hole, the other drifting in empty space. When they reunite, they might find their watches no longer match. One could have aged decades while the other barely aged at all. But relativity is just the beginning. Some quantum physicists suggest time might not even be fundamental, that it emerges from something deeper, like how temperature arises from the motion of atoms. In this view, time could be an illusion, a byproduct of how we perceive the universe rather than an intrinsic part of it. Others propose even wilder ideas, like time being a kind of fluid that flows at different rates in different places, or even the possibility of multiple timelines branching out with every decision we make. Then there's the eerie concept of block time, where past, present, and future all exist simultaneously, frozen in a four-dimensional structure. Think of it like a movie. Every frame is already there, and what we call now is just the point where the projector's light happens to be shining. If true, it means the future is already written, and free will might be nothing more than a comforting story we tell ourselves. Yet despite all these theories, time remains one of the universe's greatest mysteries. We measure it, we depend on it, and yet we still don't know if it's real or just a shadow cast by something far stranger. And if time really does flow differently across the cosmos, what does that mean for our place in it? Could entire civilizations rise and fall in what feels like an instant to us? Or might there be pockets of reality where time stands still, waiting for something or someone to set it in motion again? The answers might not just reshape physics, they could rewrite our very understanding of existence. Einstein's theory of relativity didn't just tweak our understanding of time, it rewrote the rules entirely. Imagine standing near a black hole where gravity is so intense that even light struggles to escape. Here, time doesn't just slow down, it crawls. For every hour you spend near that cosmic abyss, decades could pass for someone back on Earth. This isn't hypothetical, it's gravitational time dilation in action, a phenomenon so real that engineers have to account for it every single day. Take GPS satellites, for example. Orbiting high above Earth, they experience weaker gravity and move at staggering speeds, causing their onboard clocks to tick ever so slightly faster than those on the ground. Without constant adjustments, your navigation apps would lead you astray by miles within minutes. But what if these distortions aren't just minor corrections in our cosmic backyard? What if, in the farthest reaches of the universe, time bends so dramatically that entire civilizations could rise and fall in what feels like an eye blink to us? Picture a galaxy orbiting an ultra-dense cluster of dark matter or a rogue black hole. Time there might stretch like taffy, warping reality in ways we can barely comprehend. Some theories even suggest that in regions of extreme space-time curvature, time could loop back on itself, creating pockets where cause and effect blur into chaos. Relativity gave us the first glimpse into time's flexibility, but it might just be the opening act. If gravity can warp time, what about other forces we don't yet understand? Could dark energy, the mysterious force accelerating the universe's expansion, also be twisting time's fabric in invisible ways? The more we learn, the clearer it becomes time isn't a steady river. It's a stormy sea with currents that change depending on where you stand. And if that's true, the universe might be far stranger, far more unpredictable than even Einstein dared to dream. Black holes aren't just cosmic vacuum cleaners, they're time machines of the most extreme kind. Picture an astronaut drifting toward the event horizon, that invisible boundary where gravity's grip becomes irresistible. From our perspective, watching from a safe distance, something bizarre happens. As the astronaut gets closer, their movements slow, first to a crawl, then to a near standstill. Their spacesuit, their outstretched hand, even the light reflecting off them, all seem to freeze in place. To us, it's as if time itself has stopped for them. But here's the twist: for the astronaut, time hasn't slowed at all. From their point of view, seconds pass normally. They'd still feel their heartbeat, their breath, even as they're pulled inexorably toward the singularity. This is the paradox of black hole time dilation, where two realities exist simultaneously. The closer you get to a black hole, the more space-time stretches like taffy, warping the flow of time so dramatically that it creates what physicists call time shadows. Imagine shouting to a friend near the event horizon. Your words wouldn't just echo, they'd stretch into lower and lower pitches, red shifting into oblivion as time distorts the sound waves. Light behaves the same way, dimming and reddening until it fades from view entirely. But what if this isn't just a quirk of black holes? What if there are regions of space where time's flow is fundamentally broken? Some theories suggest that supermassive black holes, the giants anchoring galaxies, could warp time so severely that entire star systems orbit in what feels like slow motion to the rest of the universe. Civilizations might evolve, thrive, and vanish in the time it takes our sun to complete a single orbit around the Milky Way. Even stranger, certain exotic objects like naked singularities, black holes without event horizons, could create zones where time loops back on itself, trapping matter and energy in endless cycles. The implications are staggering. If time isn't uniform across the cosmos, could there be places where it's effectively paused? Imagine a rogue planet drifting through one of these frozen pockets, its surface locked in an eternal moment, its mountains and oceans unchanging for billions of years. Or consider the opposite, regions where time races ahead like a river in flood, where stars are born and die in what feels like days. Black holes force us to confront the unsettling truth. Time isn't just a backdrop to the universe. It's a fluid, dynamic thing shaped by the very fabric of space. And if these cosmic anomalies can twist it to such extremes, what else might be possible? Could the universe contain clocks that tick at 1 trillion different rates, each marking time in its own alien rhythm? The answers might lie hidden in the dark hearts of black holes, waiting for us to unravel their secrets. If relativity paints time as a smooth, flowing river, quantum mechanics suggests it might be more like a series of droplets, tiny, indivisible moments flickering in and out of existence. This isn't just a minor disagreement, it's a fundamental clash between two pillars of modern physics, each with mountains of evidence to back their claims. On one side, Einstein's relativity describes time as a malleable fabric, warped by gravity and motion, where events unfold in a seamless continuum. But quantum mechanics, the rulebook for the subatomic world, hints at a radically different possibility, that time might be pixelated, built from discrete, unbreakable chunks called chronons. Imagine watching a movie where the frames are so tiny, so rapid, that they blur into what looks like motion. What if time works the same way, with reality itself flickering at a scale we can't perceive? The conflict between these two visions isn't just theoretical, it's a puzzle that stumped physicists for decades. Relativity excels at explaining the cosmos on grand scales, from orbiting planets to colliding galaxies, while quantum mechanics masters the bizarre behavior of particles smaller than atoms. But when it comes to time, they speak different languages. Relativity says time is smooth. Quantum theory suggests it stutter steps. So who's right? Some researchers propose a middle ground, that time appears continuous to us because we're too large to notice its quantum graininess, just as a beach looks smooth from a distance but reveals countless grains of sand up close. Others go further, suggesting that time's apparent flow might emerge from deeper quantum processes, like how temperature arises from the jostling of atoms. Then there's the mind-bending idea that time might not even flow at all in the quantum realm. In certain interpretations of quantum mechanics, particles don't experience time linearly. They exist in superpositions where past, present, and future blur into a single probabilistic haze. This could mean that at the smallest scales, time loses its familiar structure, becoming more like a network of possibilities than a straight line. If true, our everyday experience of time, the steady tick of a clock, the aging of our bodies might be a kind of illusion, a macroscopic averaging of quantum chaos. The stakes for resolving this divide couldn't be higher. Unifying these theories could unlock secrets about the birth of the universe, the nature of black holes, or even whether time travel is possible. Some speculative models suggest that in the extreme conditions of the early cosmos, quantum time and relativistic time might have been indistinguishable, merging into a single, coherent framework before splintering apart as the universe expanded. Others wonder if dark energy, the mysterious force accelerating cosmic expansion, might hold clues to time's true nature. For now, the question remains open. Is time continuous or quantized? The answer might lie in experiments probing the fabric of spacetime at scales so small they defy imagination, or in observations of distant cosmic phenomena where time's quirks become visible. Until then, we're left with a tantalizing thought that the flow of time, something so fundamental to our existence, might be far stranger than we ever suspected. And if physicists can bridge the gap between these two titans of science, it won't just rewrite textbooks, it could redefine reality itself. Dark matter and dark energy, the universe's greatest mysteries, invisible forces shaping everything around us, yet completely undetectable by conventional means. Together, they make up a staggering 95% of the cosmos, while the atoms and light we can see and touch amount to little more than cosmic crumbs. But here's the real puzzle. If these shadowy substances dominate the universe, could they also be secretly twisting the flow of time itself? Take dark matter first, an unseen gravitational glue holding galaxies together. Without it, stars would fly apart like sparks from a bonfire. But some physicists speculate it might do more than just provide cosmic scaffolding. In regions dense with dark matter, could its gravitational pull subtly slow time, creating hidden pockets where clocks tick just a fraction slower? Imagine a distant galaxy shrouded in a thick halo of this mysterious substance. For any civilization living there, centuries might pass while mere decades unfold elsewhere in the universe. It's a haunting possibility, one that could explain why time seems to flow uniformly only in our local, relatively empty corner of space. Then there's dark energy, the even more elusive force driving the universe's accelerating expansion. Unlike gravity, which pulls things together, dark energy pushes space-time apart, stretching the very fabric of reality. Some theories suggest this relentless expansion might not just affect space, it could be stretching time itself, thinning it out like taffy pulled too thin. If true, the farther apart galaxies drift, the faster their local time might accelerate, as if the universe's clockwork is slowly winding down in some places while speeding up in others. Testing these ideas isn't just difficult, it's borderline maddening. Dark matter doesn't emit, absorb, or reflect light, and dark energy's effects are so subtle they're only noticeable across billions of light years. Yet scientists are devising ingenious ways to probe these mysteries. Some look for slight distortions in the light from distant supernova, hunting for hints that time's flow varies across the cosmos. Others study the cosmic microwave background, the afterglow of the Big Bang, searching for imprints of dark energy's influence on the early universe's timeline. The implications are staggering. If dark matter and dark energy truly warp time, it would mean the universe isn't just expanding, it's a patchwork of temporal zones, each ticking to its own unseen rhythm. Civilizations in dark matter, rich regions might perceive history unfolding at a glacial pace, while those in dark energy-dominated voids could witness stars flaring and dying in what feels like moments. Even stranger, if these effects aren't uniform, the very concept of a universal now could crumble, leaving us with a cosmos where simultaneity is nothing but an illusion. For now, these ideas remain tantalizing speculation, ghostly whispers at the edge of physics. But if future experiments confirm them, we might be forced to rewrite not just our understanding of time, but our place in a universe where even the most fundamental rhythms are anything but constant. What if our universe's steady march of time is just one note in an infinite symphony of temporal possibilities? Multiverse theories throw open the doors to realities where time doesn't just flow differently, it might not even play by the same rules. Picture a universe where cause and effect are reversed, where smoke pours back into a cigarette and shattered glass leaps onto tables, reassembling itself. In another, time could be a closed loop, like a record stuck on repeat, with every event destined to recur endlessly. Or imagine a reality where time doesn't exist at all, no past, no future, just an eternal, unchanging present. These aren't just thought experiments, they're serious hypotheses debated by physicists wrestling with the implications of the multiverse. the idea of parallel universes isn't new, but modern cosmology has given it teeth. Inflationary theory suggests our universe might be one bubble in a frothing cosmic foam, each bubble with its own unique physics. Some could have stronger gravity, weaker nuclear forces, or time that behaves in ways we'd find incomprehensible. Take the many worlds interpretation of quantum mechanics, where every decision spawns a new universe. In one branch, you might be reading this sentence a second earlier, in another, a century later. Time itself could branch like a tree, with each split creating a new timeline where clocks tick to different rhythms. But the wildest possibilities come from string theory, which proposes universes with extra dimensions curled into shapes we can't perceive. In some of these hidden geometries, time might not even flow linearly. It could spiral, zigzag, or fracture into disjointed fragments. Imagine a universe where time is two-dimensional, with events spreading outward like ripples on a pond, allowing for phenomena like time crystals, structures that repeat not just in space, but in time, creating perpetual motion without energy. Then there's the Boltzmann brane scenario, a chilling twist on multiverse logic. In an infinite sea of universes, there's a non-zero chance that a self-aware entity could spontaneously form, complete with false memories of a past that never existed. For such a being, time is an illusion, a narrative stitched together from chaos. It's a stark reminder that if the multiverse is real, our perception of time's arrow might be nothing more than a local quirk. The implications are dizzying. If other universes have different time laws, could they host civilizations that experience reality in reverse, watching stars coalesce from stardust and life unwind from death to birth? Or might there be realms where time is as malleable as clay, where beings can knead it into whatever shape they choose? For now, these questions linger at the edge of science, where hard data meets boundless speculation. But one thing's certain: if the multiverse is real, time is far weirder, far more flexible than we ever dreamed. And somewhere out there, in a universe unlike our own, time might be telling a story we can't even begin to imagine. Time crystals sound like something ripped from a sci-fi novel, but they're very real, and they're rewriting the rules of physics as we know them. Unlike ordinary crystals, where atoms arrange themselves in repeating patterns in space, time crystals flip the script. Their structure repeats in time, oscillating between states without any energy input, like a clock that ticks forever without ever being wound. This isn't just a theoretical curiosity. Scientists have actually created them in labs, using carefully controlled quantum systems to observe their eerie, perpetual motion. But here's the real kicker. If we can make them here, could nature have already beaten us to it? Could the universe be hiding these temporal oddities in the depths of space, where the rules of physics stretch to their limits? The idea of time crystals was first proposed in 2012 by Nobel laureate Frank Wilczek, and it sent shockwaves through the physics community. At first glance, they seem to defy one of science's most sacred laws, the second law of thermodynamics, which states that systems naturally lose energy over time, settling into disorder. But time crystals don't play by those rules. They exist in a never-ending dance, cycling through their states indefinitely, as if they've found a loophole in the universe's operating manual. Imagine a pendulum that swings back and forth forever without friction, or a river that flows upstream just as often as down. That's the level of weirdness we're dealing with. So how do they work? In the lab, researchers create time crystals by manipulating quantum systems like chains of ions or dense clouds of atoms, cooled to near absolute zero and zapped with precise laser pulses. Under these extreme conditions, the particles sync up, flipping their quantum states in a rhythmic pattern that repeats over time. untouched by entropy's usual decay. It's as if they've carved out a tiny pocket of reality where time itself becomes a playground. But the real magic happens when you consider where else this might occur naturally. Could neutron stars, with their insane gravitational pressures and quantum chaos, host time crystals in their cores? Or might the strange, warped spacetime around black holes create conditions where these structures emerge spontaneously? The implications are staggering. If time crystals exist beyond our labs, they could be cosmic clocks ticking away in the void, untouched by the expansion of the universe or the pull of gravity. They might even hold clues about time's fundamental nature, suggesting that what we perceive as a one-way flow could, under the right conditions, fold back on itself in repeating cycles. Some theorists speculate that time crystals could be the key to understanding how information escapes black holes or how quantum systems retain memory across vast stretches of time. Others wonder if there's evidence of deeper symmetries in the universe, hidden layers of physics where time isn't just a backdrop but an active participant. One thing's for certain, time crystals blur the line between science and philosophy. If matter can encode rhythms in time itself, what does that say about reality's structure? Are we living in a universe where time isn't just a river, but a mosaic of interconnected loops and pulses? For now, these questions linger at the frontier of physics, waiting for the next breakthrough. But every flicker of a time crystal in a lab brings us closer to answers, and to a truth far stranger than fiction. The Big Bang is often called the beginning of everything, but what if time itself wasn't invited to that party? Imagine rewinding the universe's clock back nearly 14 billion years, to a single, infinitely dense point where all matter, energy, and space were crushed together. Conventional wisdom says time started ticking at that exact moment, unfolding like a cosmic stopwatch the instant the universe began expanding. But here's the twist: some physicists argue time might not have had a beginning at all. It could be an eternal river flowing long before the Big Bang, with our universe just one ripple in its endless current. Take the cyclic model of the universe, for example. This theory suggests the Big Bang wasn't a true beginning, just a violent transition from a previous state. Picture two sheets of spacetime colliding like cymbals, rebounding in a fiery explosion that births a new universe. In this view, time stretches infinitely backward and forward, with no true start or end. It's as if the cosmos is breathing, expanding and contracting in cycles that could have been repeating for eternity. Supporters of this idea point to the universe's eerie uniformity, the way matter is spread so evenly across space, as evidence of a pre-bang legacy, a fingerprint of whatever came before. Then there's the no boundary proposal from Stephen Hawking and James Hartle, which imagines the Big Bang as more of a cosmic shoreline where time gently emerges from something deeper. Think of it like the North Pole. You can't travel north of it because every direction from there is south. Similarly, in this model, asking what happened before the Big Bang might be meaningless. Time, as we know it, simply didn't exist in any recognizable form. Quantum fluctuations could have spontaneously generated spacetime, meaning time didn't begin so much as crystallize into being from a froth of probabilities. But not everyone's convinced. Some theories, like loop quantum gravity, suggest time might be granular at the smallest scales, woven from indivisible chunks. If true, the Big Bang could mark the first tick of this quantum clock, a true zero point where time's fabric first stitched itself together. Others speculate about a multiverse nursery, where our universe is just one bubble in a vast, bubbling foam of realities, each with its own timeline. In that scenario, time might be infinite on a grand scale, but our local version of it began with a bang. The debate isn't just philosophical, it has real stakes for how we understand reality. If time had no beginning, the laws of physics might extend infinitely into the past, unchanged and unbroken. But if it did start at the Big Bang, that moment becomes a singularity where all known science breaks down, leaving us staring into an abyss of unknowns. Some researchers even propose wild hybrids like conformal cyclic cosmology, where the end of one universe feeds into the birth of another, stretching time into an endless Ouroboros of cosmic rebirth. For now, the question remains open, tangled in equations and competing visions of the cosmos. But one thing's clear: whether time is eternal or born from fire, its origins are far stranger than we ever imagined. And if we ever uncover the truth, it won't just rewrite our textbooks, it'll redefine what it means to exist in this vast, mysterious universe. If black holes are the universe's ultimate drains, sucking in everything that crosses their path, then white holes are their cosmic opposites, explosive fountains where matter and energy come screaming back out. Picture a black hole in reverse. Instead of an event horizon trapping light forever, a white hole would have a boundary that nothing can enter, only exit. These hypothetical objects aren't just curiosities. They're mathematical solutions to Einstein's equations of general relativity, lurking in the same physics that gave us black holes. But while black holes feel almost commonplace now, their white counterparts remain firmly in the realm of speculation. And if they do exist, they might not just defy gravity, they could flip time itself on its head. The idea of white holes raises a tantalizing question. What if time's arrow isn't fixed? In our everyday experience, time flows forward, eggs don't unscramble, and smoke never retreats into a fireplace. But white holes, if real, could challenge that certainty. Some theories suggest these objects might be black holes running backward in time, like a movie played in rewind. Imagine a black hole in one universe funneling matter into a white hole in another, creating a bridge where time's flow reverses at the threshold. For an observer outside, a white hole might appear as a sudden, violent eruption of energy, a cosmic geyser blasting particles and radiation into space with no apparent source. But here's where things get even stranger. If white holes are connected to black holes through wormholes, a concept known as an Einstein-Rosen bridge, they could create tunnels through space-time where the usual rules of cause and effect break down. Step into one end, and you might emerge in a universe where time flows backward, or where entropy decreases instead of increases. It's a scenario that feels ripped from a physicist's dream journal, yet it's grounded in legitimate math. The catch: white holes are thought to be wildly unstable, collapsing almost instantly under their own gravity, unless some exotic form of matter or energy props them up. So why haven't we found one? The universe seems to favor black holes, which form naturally when massive stars collapse. White holes, on the other hand, would require conditions so extreme they might only exist as relics of the Big Bang or as fleeting quantum flukes. Some researchers speculate that gamma-ray bursts, the most energetic explosions in the cosmos, could be white holes briefly flickering into existence before vanishing. Others suggest they might be hiding in plain sight, masquerading as mysterious cosmic phenomena we've yet to decipher. The implications are staggering. If white holes exist, they could rewrite our understanding of time's one-way street, revealing a universe where the past and future aren't so rigidly separate. They might even hint at a deeper symmetry in physics, where every black hole in our universe is paired with a white hole somewhere else, stitching reality together in ways we're only beginning to imagine. For now, white holes remain a dazzling what if, but in a cosmos where time bends and space warps, who's to say they're not out there waiting to be discovered? Wormholes have long been the stuff of science fiction, tunnels through the fabric of space-time, shortcuts bridging points light years apart or even connecting different eras. But these cosmic passageways aren't just fantasy. They emerge naturally from Einstein's equations of general relativity, the same math that predicts black holes and gravitational waves. Picture spacetime as a vast, stretchy sheet. If you fold it so two distant points touch, a wormhole could act like a needle punching through, creating a shortcut between them. One moment you're on Earth, the next you could step out near a star on the other side of the galaxy, or in another time entirely. The catch, wormholes, if they exist, would be incredibly unstable. According to general relativity, these tunnels would collapse the instant anything tried to pass through, crushed by their own gravitational forces, unless, that is, something exotic props them open. That's where theoretical physics gets wild. Some models suggest that negative energy, or exotic matter, a substance with repulsive gravity, could act like cosmic scaffolding, holding a wormhole's throat open long enough for travel. Think of it like trying to keep a hallway from collapsing by lining its walls with material that pushes outward instead of crumbling inward. The problem: we've never observed negative energy or exotic matter in nature, leaving wormholes firmly in the realm of speculation for now. But let's say we could stabilize one. The implications for time are mind-bending. Wormholes don't just connect places, they could link different moments, creating bridges between past and future. Imagine one end of a wormhole orbiting a black hole, where time slows to a crawl, while the other end sits in empty space, ticking at normal speed. After a few years, what was once a tunnel through space becomes a gateway through time. Step in one side and you might emerge decades before you left. This isn't just a quirk of math, it's a real possibility under relativity, where gravity and motion warp time itself. Yet time travel via wormhole comes with paradoxes that could unravel reality. Take the infamous grandfather paradox. If you went back and prevented your own birth, how could you have existed to time travel in the first place? Some physicists argue quantum mechanics might resolve this, with alternate timelines branching off to absorb contradictions. Others suggest the universe enforces a kind of cosmic censorship, preventing actions that would create paradoxes, like a hidden hand nudging events to keep causality intact. Even stranger, wormholes might not just distort time, they could rewrite its rules entirely. In certain theoretical models, traversable wormholes require space-time to loop back on itself, creating closed time-like curves where cause and effect circle endlessly. In such a universe, the future could influence the past just as much as the past shapes the future, blurring the line between memory and prophecy. For now, wormholes remain one of physics' most tantalizing what-ifs. They challenge our understanding of time, causality, and the very structure of reality. And while we may never find one or figure out how to keep one open, their existence in equations hints at a universe far stranger, far more interconnected than we ever imagined. Whether they're cosmic shortcuts or time-bending paradox engines, wormholes remind us that the fabric of reality may still hold surprises we've only begun to dream of. What if time isn't fundamental at all, just a shadow cast by something far stranger? The holographic principle, one of the most radical ideas in modern physics, suggests exactly that. Imagine the universe as a cosmic projection, like a movie playing on a screen. The images move, the story unfolds, but the screen itself doesn't change. In this view, time might be nothing more than an illusion, a flickering hologram generated by a deeper, timeless reality we can't yet perceive. This isn't just philosophical musing, it's grounded in cutting-edge science. The principle emerged from studying black holes, where physicists discovered something bizarre. The information describing everything swallowed by a black hole isn't lost inside it but encoded on its surface like a cosmic hard drive. Stretch this idea to the entire universe, and you get the holographic principle, the notion that all the information about our three-dimensional reality, including time, might be stored on a two-dimensional boundary at the edge of the cosmos. It's as if everything we experience, the flow of seconds, the aging of stars, the rise and fall of civilizations, is just a reconstruction of data written on some distant, invisible surface. But how could this make time an illusion? Think of a video game. The world inside the game feels vast and dynamic, with characters moving through time, but underneath, it's all just code executing on a processor. Change the code and you change the game's reality. Similarly, if our universe is a hologram, time might be a side effect of how that underlying code processes information. Events wouldn't happen in sequence. They'd exist all at once, like frames in a film strip, with our perception of time's flow coming from how we access those frames. The implications are dizzying. If time isn't fundamental, then concepts like past and future could be artifacts of our limited perspective. Some theories, like physicist Julian Barber's timeless physics, argue that everything exists simultaneously in a vast, unchanging landscape called Platonia, where what we call time is just a way of navigating between static moments. Others suggest that quantum entanglement, the spooky connection between particles across space, might be the glue holding this holographic illusion together, with time emerging from the way entangled particles update their shared information. Yet for all its elegance, the holographic principle raises thorny questions. If time is an illusion, why does it feel so real? Why do we remember the past but not the future? Some researchers propose that our brains are like quantum computers, decoding the hologram's data stream in a way that creates the sensation of time's flow. Others wonder if entropy, the universe's tendency toward disorder, might be the real force behind time's arrow, with the hologram merely reflecting that deeper asymmetry. One thing's certain, if the holographic principle is correct, reality is far weirder than we ever imagined. The ticking clock, the aging stars, the relentless march of history, all of it might be a grand illusion, a cosmic sleight of hand played out on the surface of something we're only beginning to understand. And if that's true, the next question is even more profound. What or who is running the code? Entropy is the silent architect of time's arrow, the invisible force that ensures eggs shatter but never reassemble, that coffee mixes with cream but never separates. It's why we remember the past but not the future, a cosmic rule so fundamental we barely notice it, yet it shapes everything from the lifespan of stars to the ticking of a clock. But here's the puzzle. Why does entropy always increase? And more intriguingly, could there be corners of the universe where this rule doesn't apply, where time's arrow might point in reverse or spin in circles? Think of entropy as nature's preference for messiness. Drop a sugar cube into tea and the sugar dissolves, spreading evenly, a transition from order to disorder. That's entropy in action. The second law of thermodynamics states that in any closed system, entropy never decreases. It's why ice melts in sunlight but never spontaneously refreezes in the same pattern, why sandcastles crumble but don't rebuild themselves. This relentless march toward disorder gives time its direction, its one-way street. But what if that street isn't as straight as we think? Some physicists speculate that entropy might not behave uniformly across the cosmos. In regions with extreme gravitational fields like near black holes or in the chaotic aftermath of the Big Bang, entropy's rules could twist. Imagine a universe where pockets of spacetime exist in a state of negative entropy, where energy flows backward, stitching broken glass back together or pulling smoke into a chimney. It sounds impossible, but quantum mechanics already allows for tiny, fleeting violations of thermodynamic laws on microscopic scales. Could these exceptions balloon into macroscopic phenomena under the right conditions? Then there's the mind-bending idea of Boltzmann brains, a thought experiment where random fluctuations in a high-entropy universe could, statistically, give rise to self-aware entities complete with false memories of order. If such a fluctuation occurred, would it experience time's arrow differently, perceiving entropy's increase as a localized illusion? It's a wild scenario, but it forces us to confront whether time's direction is truly universal or just a quirk of our cosmic neighborhood. Even stranger, some theories suggest that entropy's arrow might not be absolute. In a hypothetical Big Bounce universe where expansion eventually reverses into contraction, entropy could reset, rewinding time's arrow like a cosmic VHS tape. Observers in such a universe might see shattered glasses reassemble and ashes coalesce into logs, living in a reality where time's flow feels inverted. The deeper we dig, the more entropy reveals itself as more than just a measure of disorder. It's a fingerprint of time's hidden structure. And if that structure isn't uniform, the implications are staggering. Civilizations in low-entropy zones might perceive history unfolding backward, while others, nestled in high-entropy voids, could witness time accelerating like a film on fast-forward. The universe, it seems, might not have a single clock but countless, each ticking to its own rhythm, its own dance of order and chaos. Cosmic inflation is one of the most mind-bending ideas in modern cosmology. The notion that in the first fraction of a second after the Big Bang, the universe didn't just expand, it exploded outward at speeds faster than light itself. Space stretched so rapidly that regions now billions of light-years apart were once touching. But here's the real puzzle. If space could inflate faster than light, what happened to time? Did it stretch, warp, or even fracture under the strain? Picture a balloon inflating at an impossible rate, not just growing, but doubling in size every tiny fraction of a second. Now imagine that balloon is the entire universe, and the air inside is pure energy, hotter than anything we can recreate. This is inflation theory's vision of the cosmos's birth. But while we often focus on how space behaved during this frenzy, time's role is far murkier. Einstein taught us that space and time are woven together into a single fabric called spacetime. So if space could stretch beyond light speed, did time twist into knots? Some models suggest that in those first moments, time might have dilated so severely that a single tick of the cosmic clock could have felt like an eternity for an outside observer, if any could have existed. The implications are staggering. If time stretched unevenly during inflation, it could explain why the universe looks so uniform today. Tiny quantum fluctuations, magnified by inflation, became the seeds for galaxies and galaxy clusters. But if time itself was also fluctuating, those seeds might have been sown in a kind of temporal chaos, where cause and effect blurred beyond recognition. Imagine tossing a handful of confetti into a hurricane. That's how unpredictable the early universe's timeline might have been. Yet inflation isn't just about the past, it could still be shaping time today. Some theories propose that inflation never truly stopped, that our observable universe is just one bubble in an endless sea of inflating space. In other bubbles, time might flow at radically different rates, or even in reverse. It's a dizzying thought that the arrow of time we take for granted might be nothing more than a local quirk, a side effect of our cosmic address. The hunt for evidence continues. Scientists scour the cosmic microwave background, the afterglow of the Big Bang, for faint imprints of inflation's violent expansion. If they find patterns suggesting spacetime was stretched to its limits, it could mean time itself was once as malleable as putty, and might still be, in corners of the universe we've yet to explore. One thing's certain, if inflation really did warp time as fiercely as space, our understanding of reality is in for a revolution. The universe's first moments weren't just hot and dense, they might have been a place where time itself lost all meaning. Neutron stars are nature's ultimate pressure cookers, cosmic remnants so dense that a single sugar cube of their material would weigh as much as a mountain. Born from the explosive deaths of massive stars, these city-sized powerhouses pack more mass than our Sun into a sphere barely 20 kilometers across. But it's not just their density that bends the mind, their gravity warps time itself. Stand on the surface of a neutron star, and you'd experience time crawling at a fraction of the rate it does on Earth. A clock ticking there might lose hours compared to one in deep space, all thanks to the star's crushing gravitational field. This isn't just theoretical. In 2017, astronomers witnessed a neutron-star merger, an event so violent it sent ripples through spacetime itself. The gravitational waves detected from that collision carried fingerprints of extreme time dilation, confirming Einstein's predictions with stunning precision. But here's the twist: neutron stars don't just bend time, they push relativity to its breaking point. At their cores, matter is squeezed so tightly that protons and electrons fuse into a sea of neutrons, creating conditions where quantum mechanics and gravity collide in ways we still don't fully understand. Some theories suggest their cores might harbor even stranger states, quark-gluon plasma, or perhaps free-floating quarks that defy the very concept of solid matter. The most baffling possibility: neutron stars might function as natural time machines. Picture a spaceship orbiting one at just the right distance, skimming the edge of its gravitational well. Time for the crew would slow so dramatically that while they experience a single year, centuries could pass back on Earth. It's a one-way trip to the future, no fancy technology required, just the raw, unfiltered power of spacetime curvature. Even stranger, some models suggest that rapidly spinning neutron stars, called pulsars, could create frame-dragging effects so intense they twist spacetime into knots, potentially opening paths to closed time-like curves, loops where time circles back on itself. Yet for all their time-bending potential, neutron stars guard their secrets fiercely. Their surfaces are likely crusted with iron mountains no taller than a fingernail, yet harder than diamond, while their magnetic fields are trillions of times stronger than Earth's, powerful enough to rip atoms apart from thousands of kilometers away. These extremes make them cosmic laboratories for testing physics under conditions we could never recreate on Earth. Every flicker of their X-ray emissions, every pulse of their radio beams carries clues about how time, gravity, and matter behave at the edge of impossibility. So could we ever harness a neutron star's time-warping power? For now, it's pure speculation. The energy required to reach one, let alone survive its wrath, is beyond our wildest dreams. But their very existence proves that time isn't just a universal constant, it's a fluid, shaped by the cosmos itself. And if these stellar relics can twist time so dramatically, who's to say what other temporal wonders might be hiding in the universe's darkest corners? The silence of the cosmos isn't just puzzling, it's deafening. With billions of galaxies, each teeming with stars and planets, the universe should be buzzing with civilizations. Yet, as physicist Enrico Fermi famously pointed out, we've found no trace of them. This contradiction, known as the Fermi paradox, has haunted scientists for decades. But what if the answer isn't about where aliens are, but when? If time flows differently across the cosmos, entire civilizations might rise and fall in cosmic eye blinks, their signals fading before we even think to listen. Consider this: Earth is a relative newcomer in a 13.8 billion-year-old universe. Intelligent life here took 4 billion years to evolve. Now imagine a planet orbiting a star near a supermassive black hole where time crawls due to extreme gravity. While we've been building pyramids and launching rockets, they might have only just discovered fire or already transcended into forms we can't comprehend. The opposite could also be true. In regions where dark energy dominates, stretching space-time like taffy, time might race forward. A civilization there could have flourished and vanished billions of years before Earth even formed. The universe's timeline isn't uniform, it's a patchwork of tempos, and we might simply be out of sync with everyone else. This leads to an even darker possibility. Time itself could be the great filter, the invisible barrier that prevents civilizations from lasting long enough to meet. Maybe the window for contact is impossibly narrow. Imagine two ships passing in the night, one sailing at dawn, the other at dusk, never close enough to see each other. If cosmic time zones scatter civilizations across millennia, the odds of overlapping become vanishingly small. Some might self-destruct before achieving interstellar travel, while others evolve beyond physical form, leaving no traces we'd recognize. Yet there's hope in the chaos. If time's flow is variable, the universe could be filled with civilizations, just not in ways we expect. They might communicate via quantum entanglement, bypassing the speed of light, or encode messages in pulsar bursts that repeat every million years. Our mistake could be assuming everyone marks time the same way. The silence isn't empty, it's a symphony playing in rhythms we haven't learned to hear. And if we're patient or clever enough to adjust our clocks, we might yet find our place in the cosmic chorus. Quantum entanglement is one of the most baffling phenomena in physics, a ghostly connection that defies everything we know about time and space. Picture two electrons spinning in perfect sync, created together in the same quantum event. Separate them by light years, and they remain inexplicably linked. Measure one's spin as up, and its partner instantly becomes down, no matter the distance. Einstein called this spooky action at a distance, a phrase that perfectly captures the unease physicists still feel about how entanglement shreds our classical notions of cause and effect. What makes entanglement so unsettling is its disregard for time itself. In our everyday experience, information can't travel faster than light. It's the universe's ultimate speed limit. But entangled particles seem to communicate instantaneously, as if space and time don't apply to them. Imagine tossing a pair of gloves into separate black holes on opposite sides of the galaxy. Open one box to find a left-handed glove, and you'd instantly know the other holds its right-handed twin, even though no signal could have crossed that distance. This isn't just theoretical. Experiments have confirmed it time and again, leaving scientists grappling with a reality where now might be a local illusion. Some theorists propose that entanglement hints at a deeper layer of existence, a substratum where time and space emerge from something more fundamental. Think of the universe as a vast network, with entangled particles as nodes connected by invisible threads. In this view, what we perceive as separate events in time could actually be reflections of a timeless, interconnected whole, like ripples on a pond tracing back to a single stone. It's a radical idea that the flow of time might be a side effect of how we observe this quantum web, not an intrinsic feature of reality. The implications ripple outward. If entanglement transcends time, could it be used to build a quantum internet where messages arrive before they're sent? Not exactly, while the correlation between particles is instantaneous. We can't control which state each particle takes, making faster-than-light communication impossible. But there's a tantalizing possibility that entangled particles might remember their shared past in ways that distort our perception of time's arrow. Experiments with delayed choice quantum erasers suggest that measurements made in the present can retroactively influence entangled particles' behavior in the past, as if time loops back on itself at the quantum scale. Even stranger, entanglement might not be limited to pairs of particles. The universe could be teeming with quantum knots, complex systems where countless particles are entangled in intricate webs. In such a network, time's flow could become as flexible as a spider's silk, bending and twisting in ways we've yet to imagine. Some models even suggest that black holes preserve information about what falls into them by encoding it in entangled particles on their surfaces, a holographic ledger where time's usual rules don't apply. The more we learn, the clearer it becomes. Entanglement isn't just a quirk of tiny particles. It could be the scaffolding of reality itself, a hidden architecture where time is just one thread in a far grander tapestry. And if that's true, the universe might be far more interconnected, far more mysterious than we ever dared to dream. Simulation theory turns our understanding of time inside out. What if the seconds ticking by aren't fundamental, but lines of code in some vast cosmic program? Imagine the universe as an ultra-advanced simulation where time isn't a river flowing on its own, but a variable carefully controlled by whatever or whoever is running the system. In this view, the past, present, and future might not even be real, just data points rendered in sequence to create the illusion of continuity, like frames in a video game. Every sunrise, every heartbeat, every galaxy spinning in the void could be part of an elaborate calculation, with time itself acting as the processor's clock speed. This isn't just sci-fi speculation. Philosophers like Nick Bostrom have laid out compelling arguments for why our reality might be a simulation, pointing to the staggering pace of technological advancement. If civilizations eventually gain the power to create hyper-realistic virtual worlds, the odds tilt heavily toward us living in one of them rather than the original, base reality. And if that's true, time as we know it could be entirely artificial, a tool designed to give the simulation structure and order. Think of it like the ticking of a computer's internal clock, synchronizing events so everything runs smoothly. Without it, the simulation would collapse into chaos, but here's where things get eerie. If time is programmed, could there be glitches in the system? Reports of déjà vu, time slips, or even bizarre coincidences that defy probability might be more than just quirks of human perception. They could be bugs in the code. Consider the famous Mandela effect, where large groups of people misremember historical details identically. Could these inconsistencies be patches or updates applied unevenly across the simulation? Even more unsettling, if time is adjustable, could those running the simulation rewind it, speed it up, or pause it altogether without us ever noticing? The implications stretch beyond philosophy. Physicists are already testing simulation theory by looking for pixelation in reality, tiny, fundamental limits to space and energy that might hint at underlying code. If time is similarly quantized, broken into discrete steps too small for us to perceive, it could explain why certain quantum phenomena appear to operate outside classical causality. Some researchers even suggest that black holes might function like cosmic garbage collectors, compressing data to free up processing power, a wild but tantalizing idea. Yet the most profound question remains: if time is artificial, does free will exist at all? Or are we just characters in a pre-rendered story, following scripts written in some higher dimensional programming language? Simulation theory doesn't just challenge our place in the universe, it forces us to wonder whether the flow of time, something so deeply woven into our existence, is nothing more than an elegant illusion. And if that's the case, the next question is unavoidable. Who or what is pressing play? Time itself might not be eternal. It could have an expiration date. Picture a universe so old that all stars have burned out, black holes have evaporated, and even the last flickers of light have faded into an endless, icy darkness. This is the heat death of the cosmos, a state of maximum entropy where energy is evenly spread, and nothing can ever change again. In this frozen future, time wouldn't just slow down, it would lose all meaning. Without differences in energy, without events to mark its passage, time would become like a broken clock, its hands motionless forever. But how could something as fundamental as time just stop? Think of entropy as the universe's battery running down. Every process, stars shining, planets orbiting, even thoughts forming in your brain relies on energy flowing from high to low states, creating pockets of order in a sea of chaos. But eventually that energy evens out. Imagine stirring cream into coffee until it's perfectly uniform. No swirls remain, no gradients, just a featureless beige. At that point, no more work can be done, no more stories can unfold. Time, in any meaningful sense, ceases to exist. Yet there's a haunting question: could some corners of the universe cheat this fate? Quantum fluctuations, tiny, random blips in energy, might occasionally create temporary pockets of order, like ripples in an otherwise still pond. In an eternally expanding cosmos, these fluctuations could, statistically, give rise to Boltzmann brains, self-aware entities that flicker into existence just long enough to perceive a phantom reality before dissolving back into the void. It's a chilling thought. Even in a dead universe, fragments of consciousness might briefly convince themselves they're alive, their subjective time existing in defiance of the greater stillness. Alternatively, what if our universe isn't alone? If the multiverse is real, other universes might follow entirely different rules, some collapsing in fiery crashes, others cycling endlessly through birth and rebirth. In those realms, time could be as resilient as gravity, eternally resetting like an hourglass flipped anew. Or consider the wild possibility of baby universes budding off from black holes, each inheriting a twisted version of their parent's spacetime. If time is mortal in our universe, it might be immortal in another. The heat death isn't just a distant doom, it's a mirror held up to time's true nature. If time can end, was it ever real to begin with, or just a side effect of energy's uneven distribution? And if some regions escape the freeze, does that mean time is less a universal constant and more a local phenomenon, as variable as the weather? The answers might lie not in the far future, but in the fabric of reality itself, waiting for us to unravel them before the clock runs out. The idea of a universe trapped in an endless loop, expanding, collapsing, and reborn in a fiery blaze feels like something from ancient mythology. Yet this vision of a cyclic cosmos isn't just poetic. It's a serious scientific hypothesis with roots in cutting-edge physics. Imagine the universe not with a single dramatic Big Bang, but as a cosmic accordion, breathing in and out across eons, each collapse birthing a new expansion in an infinite dance of destruction and creation. But here's the twist: if the universe truly cycles, what happens to time? Does it reset like a stopwatch with each new bang, or does some deeper thread of history carry through, weaving a tapestry across cycles? The concept of cyclic universes isn't new. Ancient Hindu cosmology spoke of cosmic cycles lasting trillions of years, while Stoic philosophers imagined a universe reborn identically each time down to the last grain of sand. Modern physics gives this poetry equations. Some models, like Roger Penrose's conformal cyclic cosmology, propose that the universe's far future, a cold, empty expanse stripped to photons, might mathematically resemble the ultra-smooth, energy-dense state of the Big Bang. In this view, the end of one epoch could literally become the beginning of the next, with time itself losing all scale at the transition. It's as if the universe hits a cosmic reset button, but the old data isn't erased, just compressed beyond recognition. Evidence for this bold idea is sparse but tantalizing. Penrose and others have scoured the cosmic microwave background, the afterglow of the Big Bang, for faint, circular patterns they claim could be gravitational wave imprints from collisions of supermassive black holes in a previous universe. These Hawking points remain controversial, but if confirmed, they'd be fossils of a cosmos that existed before our own. Even stranger, some cyclic models suggest that dark energy, the force accelerating the universe's expansion, might weaken over time, allowing gravity to eventually reverse the expansion and trigger a big crunch. In this scenario, time wouldn't so much end as pivot, like a pendulum reaching the top of its arc before swinging back. But the most mind-bending question isn't whether the universe cycles, it's whether we do. If time truly resets with each bang, does every cycle replay the same events, the same stars, the same civilizations rising and falling in perfect repetition? Or could subtle differences creep in, making each iteration a variation on a theme? Quantum mechanics throws fuel on the fire. If randomness is baked into reality, no two cycles could ever be identical. Though you reading this now might have lived 1,000 variations before, each with slightly different choices, a cosmic game of dice played on the grandest scale. Critics argue that cyclic models face thorny problems. Entropy, the measure of disorder, has been increasing since the Big Bang, so how could a collapsing universe clean the slate enough for a fresh start? Some theorists propose that black holes act as cosmic shredders, erasing information and resetting entropy at the crunch. Others suggest the universe expands so vastly between cycles that entropy per volume effectively dilutes to zero, like spreading a drop of ink across an ocean. But these are speculative fixes, and until we understand quantum gravity or the true nature of dark energy, the debate rages on. Whether the universe cycles or not, the idea forces us to confront time's deepest mystery. Is it a stage or part of the play? If time transcends individual cycles, then our universe's story might be just one chapter in an infinite volume epic. But if each bang is a hard reboot, then time itself could be as fleeting as the galaxies it carries, a local phenomenon, born and dying with every turn of the cosmic wheel. Either way, the lesson is humbling. The rhythms we take for granted, the steady tick of seconds, the aging of stars, might be mere footnotes in a saga so vast it makes eternity look small. Kurt Gödel, one of the greatest minds of the 20th century, didn't just revolutionize mathematics, he cracked open Einstein's equations and found something hidden inside that even Einstein himself hadn't anticipated. A universe where time doesn't march forward in a straight line, but loops back on itself like a twisted ribbon. Imagine setting out on a journey through space only to return to your own past, meeting a younger version of yourself before you ever left. This isn't science fiction. It's a legitimate solution to the equations that govern reality, a cosmic glitch where cause and effect tangle into knots. Gödel's universe is a place where time travel isn't just possible, it's unavoidable. The key to this bizarre possibility lies in what physicists call closed time-like curves, paths through space-time that circle back to their own starting point. Think of it like hiking up a mountain only to find the trail spirals in such a way that you end up right where you began, but at an earlier moment in time. In Gödel's solution, the entire universe is rotating, dragging space-time along with it like a whirlpool. If you move just right within that cosmic swirl, you could hitch a ride on the curvature of reality itself, returning to your own past as effortlessly as a leaf caught in an eddy. But here's the catch: Gödel's universe isn't our universe. The math checks out, but observations show the cosmos isn't rotating as a whole, at least not in a way that would create these time loops. So does that mean closed time-like curves are just a mathematical oddity, a quirk of theory with no real-world relevance? Not necessarily. Similar loops could exist in extreme environments, like near the swirling maelstrom of a rotating black hole, or in the presence of unfathomably dense cosmic strings, hypothetical defects in spacetime thinner than an atom but with the mass of a star. In these warped pockets of reality, time might fold back on itself, creating shortcuts to the past. The implications are staggering. If closed time-like curves exist, even in theory, they throw causality into chaos. The grandfather paradox, where you go back in time and prevent your own birth, is just the start. What if a scientist receives a message from their future self with the secret to time travel, builds the machine, and then sends that same message back? Who invented the idea? Where did the information come from? The universe might resolve these paradoxes by allowing only self-consistent loops, where events in the past and future lock together like puzzle pieces, leaving no room for contradictions. Yet, even if nature forbids these loops, Gödel's work forces us to confront a profound question. Is time travel inevitable in some corner of the multiverse? If Einstein's equations permit it under certain conditions, does that mean somewhere, in some alternate reality, time is a tangled web rather than an arrow? The answer might depend on whether the universe plays by strict rules or if it's willing to bend them or break them entirely when we're not looking. One thing's certain: in the shadow of Gödel's spinning cosmos, time is far stranger, far more malleable than our clocks and calendars could ever suggest. String theory doesn't just suggest there's more to the universe than meets the eye, it insists on it. Hidden beneath the familiar 3 dimensions of space and the steady tick of time, this radical framework proposes at least 6 more dimensions, curled into shapes so tiny they evade detection. But what if these extra dimensions aren't just spatial? What if some of them are temporal, folding time itself into geometries we can't even imagine? Picture time not as a straight line but as a vast, multidimensional tapestry. In string theory's vision, every particle in the universe is a vibrating string, and the notes it plays depend on how it moves through these hidden dimensions. Some vibrations might correspond to particles we know, like electrons or photons, while others could represent entirely new forms of matter, or even alternate versions of time itself. Imagine a dimension where time spirals like a corkscrew, looping back on itself in ways that defy our linear experience, or one where time branches like a tree, with every possible past and future coexisting in a tangled web of probabilities. The implications are staggering. If time has extra dimensions, causality, the idea that causes must precede effects, might not be the ironclad rule we think it is. Events in our timeline could be shadows cast by higher dimensional interactions, like ripples from a stone tossed into a pond we can't see. Some models even suggest that black holes might be bridges to these layered timelines, their singularities punching through to realms where time flows backward or in loops. It's as if the universe has been hiding a secret library of histories, each shelved in a dimension just beyond our grasp. But how could we ever test such a mind-bending idea? String theory's extra dimensions are notoriously elusive, compacted to scales a billion times smaller than an atom. Yet there's a tantalizing possibility. If these dimensions influence how strings vibrate, they might leave faint fingerprints in the fabric of spacetime itself. Gravitational wave detectors like LIGO could one day catch echoes of higher dimensional echoes in the ripples from colliding black holes, or particle colliders might uncover hints of hidden temporal dimensions in the debris of high-energy collisions. The most radical interpretation, our experience of time as a one-way street might be an illusion, a side effect of being trapped in a single slice of a far richer reality. In the full, unfurled dimensions of string theory, past, present, and future could exist simultaneously, not as a block universe, but as a living, breathing structure where every moment is a note in an infinite symphony. Whether that symphony has a conductor or whether time's dimensions compose themselves remains one of the deepest mysteries in physics. One thing's certain: if string theory is right, time isn't just something we measure, it's something we're embedded in, like fish swimming through unseen currents. And those currents might be far stranger than we ever dreamed. In the late 1970s, NASA Pioneer 10 and 11 spacecraft did something bizarre. They started slowing down. Not from friction or some mechanical failure, but as if an invisible hand was gently pressing the brakes. Scientists called it the Pioneer anomaly, a tiny but persistent deviation from their predicted trajectories. At first, the numbers seemed insignificant, a drift of about 300,000 miles over a decade. But in the precise world of orbital mechanics, even a whisper of unexpected deceleration raises alarms. For years, physicists scrambled for explanations, from leaks in the probe's fuel systems to the faint push of heat radiating off their surfaces. But what if the answer wasn't about forces at all? What if time itself was playing tricks on the pioneers? General relativity tells us that gravity slows time. The stronger the gravitational field, the more clocks drag. Near Earth, the effect is minuscule, but over vast distances, it adds up. Some researchers speculated that if the solar system's gravitational field wasn't perfectly uniform, if pockets of denser spacetime lurked in the outer reaches, time might have ticked slightly slower for the pioneers than for Earth's tracking stations. That subtle dilation could make the probes appear to decelerate from our perspective, even as their onboard clocks recorded normal speeds. It's like watching a runner from a distance while standing on a slowing treadmill. Their pace seems to drop, but only because your own sense of time has shifted. Yet the math never quite lined up. The anomaly was too small to match known gravitational variations, and no cosmic structures massive enough to warp local time were found in the probe's path. Then, in 2012, a team analyzing decades of thermal data made a breakthrough. Uneven heat radiation from the spacecraft's power systems could explain most of the drift. Case closed, it seemed, until deeper analysis revealed the heat theory still left gaps. The anomaly wasn't fully solved, just nudged into the shadows. This leaves us with a tantalizing thought. Could the pioneers have stumbled into a region where time's flow was subtly distorted? Not by gravity alone, but by something else: dark matter clumping along their trajectory, or an unseen relic from the solar system's formation, warping spacetime in ways we don't yet understand. The probes are now silent, drifting toward the stars, but their mystery lingers. If time's variability isn't just a cosmic scale phenomenon but flickers in our own celestial backyard, what other secrets might be hiding in the quiet between the planets? The Pioneer's unexplained drift could be more than a glitch. It might be the first faint signal that time's rhythm is far less predictable than we ever imagined. Gamma-ray bursts are the universe's most violent explosions, brief, blinding flashes of energy so intense they outshine entire galaxies for a few terrifying seconds. Born from collapsing stars or colliding neutron stars, these cosmic detonations pack more power than our Sun will emit in its entire 10 billion-year lifetime. But beyond their raw destructive force, gamma-ray bursts might hold an even stranger secret: the ability to twist time itself. Picture the aftermath of one of these cataclysms. As the burst tears through space at near light speed, its energy doesn't just radiate outward, it warps the very fabric of spacetime around it. According to general relativity, Such an immense concentration of energy should create gravitational waves, ripples in spacetime that subtly stretch and compress everything in their path. But some theorists suggest the effect could be far more dramatic. If a gamma-ray burst erupts close enough to a black hole or neutron star, its energy might amplify existing spacetime curvature, creating temporary time lenses where clocks tick at wildly different rates across short distances. Imagine two astronauts floating near the burst. One might experience a minute while the other lives an hour, their perception of reality fractured by the explosion's aftermath. The real puzzle lies in the burst's ultra-relativistic jets, narrow beams of particles racing outward at 99.9% the speed of light. At these velocities, time dilation effects become extreme. For particles in the jet's core, seconds could stretch into years compared to our reference frame. This raises a haunting possibility. What we observe as a fleeting burst might actually be a slower motion echo of an event that unfolded over much longer periods from the jet's perspective. It's like watching a strobe light from a speeding train. The flashes seem instantaneous to us, but their source experiences time differently. Even stranger, certain gamma-ray bursts exhibit quasi-periodic oscillations, subtle, repeating patterns in their light curves that some physicists interpret as evidence of spacetime ringing like a bell. If spacetime can vibrate, could these oscillations create localized time loops where brief moments repeat like a stuck record? The math hints at this possibility, though no observations have confirmed it yet. Still, the idea isn't pure speculation. In 2019, astronomers detected gravitational waves from a neutron star collision that also produced a gamma-ray burst, a smoking gun linking these events to spacetime's fundamental distortions. The implications ripple across cosmology. If gamma-ray bursts can warp time, even fleetingly, they might serve as natural laboratories for testing quantum gravity, the holy grail of physics. Their extreme energies could reveal how spacetime behaves at the smallest scales, where Einstein's smooth continuum might shatter into a froth of quantum bubbles. Some models even suggest that certain bursts could produce microscopic wormholes, stitching together distant moments in time like cosmic thread. Yet for all their destructive power, gamma-ray bursts might also be cosmic timekeepers. Their predictable light curves, brightening and fading in distinct patterns, could allow future civilizations to synchronize clocks across galaxies, using these explosions as universal reference points. In a universe where time flows differently everywhere, these fleeting flares might be the only constant lighthouses in the stormy sea of relativity. The next time a gamma-ray burst lights up the sky, remember, you're not just witnessing a star's death throes. You might be seeing time itself bend under the weight of the universe's most violent energy. And if we ever learn to read those distortions, they could reveal secrets about reality that dwarf even the burst's unimaginable power. Dark flow is one of the most puzzling mysteries in modern cosmology, a strange, unexplained current sweeping entire galaxy clusters toward some unseen horizon at staggering speeds. Imagine dropping dye into a still pond and watching it stream relentlessly in one direction, defying the stillness around it. That's what astronomers observed when they mapped the motion of hundreds of galaxy clusters. An eerie, coordinated movement towards something beyond the edge of our observable universe. The culprit no one knows for sure, but one provocative theory suggests this cosmic river isn't being pulled by gravity alone. It might be riding a hidden gradient in time itself. The discovery of dark flow dates back to 2008, when researchers studying the cosmic microwave background, the afterglow of the Big Bang, noticed something bizarre. Galaxy clusters weren't just drifting randomly, they were streaming at over 2 million miles per hour toward a specific patch of sky, as if drawn by an invisible hand. This wasn't just statistical noise. The clusters spanned billions of light years, far too vast for any known gravitational force to orchestrate their motion. The leading explanation: a gravitational anomaly beyond our cosmic horizon, perhaps a supermassive structure lurking in the unobservable universe, its pull warping spacetime like a magnet tugging iron filings. But here's where time enters the equation. If gravity can bend time, as Einstein showed, then a structure massive enough to drag galaxies might also warp the local flow of time around it. Picture a slope where time runs faster at the top and slower at the bottom. Galaxies caught in this gradient would naturally slide toward the slower time region, just as water flows downhill. In this scenario, dark flow isn't just a spatial current, it's a temporal one, with galaxies migrating toward where time drags its feet. It's as if the universe has a subtle tilt, and everything is rolling toward the slowest ticking clock. The implications are staggering. If time's flow varies on cosmic scales, it could mean our universe is far more lopsided than we thought. Most models assume a uniform, isotropic cosmos, where the laws of physics hold steady in every direction. But dark flow hints at a grand asymmetry, a fundamental unevenness woven into the fabric of reality. Some theorists even speculate that this gradient could trace back to the Big Bang itself, a relic of some primordial imbalance that set time's tempo differently in different regions. Critics argue that dark flow might be an illusion, a systematic error in interpreting cosmic microwave data. Yet repeated observations, including studies of galaxy clusters using X-ray telescopes, continue to find the same mysterious motion. If it's real, the question isn't just what's pulling the galaxies, it's why. Could a neighboring universe be exerting gravitational influence through some higher dimensional bridge? Or is our cosmos embedded in a larger structure, like a bubble in a foam, where time's rules shift at the edges? The most haunting possibility: dark flow might be evidence of a universe where time isn't just relative, it's alive, dynamic and textured, with currents and eddies we've only begun to map. If so, the galaxies aren't just being pulled through space, they're being carried by time itself, swept along in a river whose source and destination remain hidden in the cosmic dark. And if that's true, the flow might not be the only thing that's dark. Our understanding of time's true nature could be just as shadowed. Vacuum decay isn't just a cosmic catastrophe, it's a silent, invisible rewiring of reality itself. Picture the universe as a vast, unstable hillside, where the ground beneath our feet isn't solid rock but fragile soil. Right now, we're standing on what physicists call a false vacuum, a seemingly stable state that could, at any moment, collapse into something far more fundamental, a true vacuum. And if that happens, the domino effect wouldn't just destroy matter or energy, it would erase the very laws of physics, including time as we know it. Here's how it works. Quantum field theory suggests that what we perceive as empty space isn't empty at all. It's a seething quantum foam where particles flicker in and out of existence, governed by invisible energy fields. These fields exist in specific configurations, like valleys in a rolling landscape. Our universe currently sits in a shallow valley, the false vacuum, but there might be a deeper, more stable valley far below. If a tiny region of space quantum tunnels into that lower state, it would create a bubble of true vacuum. Inside that bubble, the fundamental constants, the speed of light, the strength of gravity, even the arrow of time, could be completely different. The terrifying part: this bubble would expand at nearly light speed, its boundary a wall of pure energy rewriting spacetime as it passes. One moment you'd exist, the next the rules that define your existence would vanish. Stars, planets, even the fabric of causality would dissolve into a new reality where concepts like before and after might not apply. There'd be no warning, no explosion, just an unstoppable wave of annihilation, leaving no trace of the universe as it was. But is this just theoretical doom-mongering? Shockingly, the math checks out. In 2012, researchers calculated that the Higgs field, the same field that gives particles mass, might indeed be metastable, hovering in a false vacuum state. If correct, vacuum decay isn't just possible, it's statistically inevitable given enough time. The only comfort, the half-life of our vacuum could be billions of times longer than the current age of the universe. Then again, it might have already happened somewhere beyond our cosmic horizon, its lethal bubble racing toward us at light speed, the truly bizarre twist. If vacuum decay occurs, we'd never see it coming. The bubble's boundary would move so fast that the first sign of its arrival would be instant oblivion. No light, no signal could outrun it. Some theories even suggest that the process might have already begun in distant galaxies, their light still traveling toward us, unaware their home no longer exists in any recognizable form. Yet vacuum decay isn't just a doomsday scenario, it's a window into the universe's deepest workings. If our vacuum is metastable, it implies the existence of other, more stable states where physics operates entirely differently. That raises an eerie possibility. Our universe's laws might not be fundamental but accidental, a fleeting configuration in a multiverse of infinite possibilities. And if that's true, time itself might be far more fragile than we ever imagined. So while vacuum decay remains a remote threat, its implications are immediate. It forces us to confront the unsettling truth that reality's rules aren't written in stone, they're written in something far less permanent. And somewhere out there, in the infinite dark, the universe might already be forgetting them. Bose-Einstein condensates are like time's funhouse mirrors, places where the familiar rules of physics twist into something surreal. Imagine cooling a gas of atoms to just a hair above absolute zero, the coldest temperature possible. At this extreme, atoms lose their individuality, merging into a single quantum entity that moves in eerie unison. It's as if trillions of particles suddenly decide to dance as one, their collective rhythm so precise that time itself seems to slow to a crawl. In this bizarre state, light passing through the condensate slows to bicycle speeds, and quantum effects normally hidden at microscopic scales become visible to the naked eye. But here's the real mystery. If we can create these time-bending conditions in the lab, could nature have already beaten us to it, deep in the freezing voids between galaxies, or in the shadowy outskirts of neutron stars? Pockets of ultra-cold matter might exist under similar conditions. Picture a rogue gas cloud drifting through the cosmos, chilled by the endless expansion of space until it stumbles into the quantum twilight zone. In such a place, atoms wouldn't just move slowly, they'd exist in a state where time's arrow blurs and entropy's march hesitates. The implications stretch beyond curiosity. If Bose-Einstein-like condensates form naturally in space, they could act as cosmic lenses for time, distorting our view of distant events. Light from a star passing through such a region might arrive stretched and warped, its signals delayed not by distance alone, but by the condensate's time-slowing grip. Astronomers might even mistake these delays for signs of dark matter or hidden black holes, unaware they're seeing the fingerprints of quantum time dilation. Yet the strangest possibility lies in entanglement. In a Bose-Einstein condensate, particles are so deeply linked that measuring one instantly affects the others, no matter how far apart they are. If similar entanglement occurs in cosmic condensates, it could create networks where time's flow is synchronized across light years, or scrambled into chaos. Imagine two stars, each orbiting a condensate-rich nebula, their clocks inexplicably ticking in perfect sync despite being separated by millennia of space. The more we learn, the clearer it becomes. Time isn't just something we measure. It's a fluid shaped by the quantum dances of matter itself. And if condensates teach us anything, it's that in the coldest corners of reality, time might not just slow down, it could rewrite its own rules. The Planck Epoch is where physics as we know it breaks down, a realm so extreme, so alien, that even time itself might not have existed yet. Picture the universe less than a trillionth of a second old, compressed into a space smaller than a single atom, with temperatures surpassing 100 million trillion degrees. Here, the energy was so intense that gravity ceased to behave as a gentle force and instead became as volatile as the other fundamental forces, merging with them in a quantum frenzy. In this primordial chaos, the familiar ticking of cosmic clocks would have been meaningless. There was no before or after, just a seething, formless potential where space and time were not yet distinct, but knotted together in a froth of uncertainty. To grasp this timeless state, imagine standing in a pitch-black room with no walls, no floor, no sense of up or down. Now remove even the possibility of movement, of change, of sequence. That's the Planck Epoch, a phase where the very concept of time loses its footing. Quantum fluctuations weren't just happening in time, they were time flickering in and out of existence like static on a screen. Some theories suggest that what we now perceive as time's arrow emerged from this chaos like a thread pulled from a tangled knot, a direction crystallizing from the randomness as the universe cooled. Others propose that time didn't begin so much as it condensed, like dew forming on a leaf, from a deeper, timeless layer of reality. The transition from timelessness to time is one of cosmology's greatest mysteries. Just as ice melts into water, the Planck Epoch melted into the universe we recognize, but the exact moment when time snapped into focus remains hidden. Some models hint that gravity's separation from the other forces, a process called symmetry breaking, acted like a cosmic starting gun, carving spacetime from the quantum foam. Others speculate that time emerged in quantized chunks, like pixels resolving into an image, with the Planck time 10 to the minus 43 seconds, marking the smallest possible unit of this fledgling chronology. Yet the most radical idea is that time might not be fundamental at all. Just as temperature arises from the motion of particles, time could be an emergent property, a collective illusion generated by the universe's underlying quantum structure. In this view, the Planck Epoch wasn't a beginning, it was a phase shift, a moment when the cosmos remembered how to keep track of itself. If true, the real question isn't how time began, but how we became convinced it was always there. The echoes of this epoch linger in the universe's oldest light. The cosmic microwave background, a snapshot of the infant cosmos, carries faint imprints of quantum fluctuations that may have been time's first whispers. By studying these patterns, physicists hope to glimpse the rules that birthed time itself, or discover that our linear chronology is just one note in a far stranger symphony. One thing's certain, the Planck Epoch challenges us to rethink not just the origin of time, but what time even is. And somewhere in that primordial fire, the answer might still be waiting, frozen in a moment before moments began. Tachyons sound like something straight out of science fiction, particles that don't just break the speed limit of the universe but shatter it, moving faster than light itself. According to Einstein's theory of relativity, nothing with mass can reach light speed, but tachyons, if they exist, would have a bizarre property. They're born faster than light and slow down as they gain energy, flipping our intuition about motion on its head. Even stranger, their relationship with time isn't just unconventional, it's inverted. For a tachyon, time might not flow forward at all. Instead, these hypothetical particles could experience time backward, arriving at their destination before they even depart. The idea of faster-than-light particles isn't new. Physicists first toyed with the concept in the 1960s, when quantum field theory revealed that certain equations allowed for particles with imaginary mass, a mathematical quirk that would make them inherently superluminal. Unlike ordinary matter, which requires infinite energy to reach light speed, tachyons would need infinite energy to slow down to it. But here's the twist: if tachyons exist, they wouldn't just defy speed limits, they'd upend causality itself. Imagine a tachyon message sent from Earth to a distant star. According to some interpretations of relativity, observers in certain reference frames could see that message arrive before it's sent, creating a paradox where effect precedes cause. So why haven't we found them? Despite decades of searching, from particle colliders to cosmic ray detectors, tachyons remain stubbornly theoretical. Some experiments have hunted for their signatures in high-energy collisions, looking for anomalies in energy distributions that might hint at their existence. Others have scoured the cosmos for patterns in gamma-ray bursts or quantum noise that could betray the presence of these elusive particles. So far, the results are silent, but absence of evidence isn't evidence of absence. Tachyons, if real, might interact so weakly with ordinary matter that they're effectively invisible to our instruments, slipping through the cracks of reality like ghosts. Yet the implications of their existence are too tantalizing to ignore. If tachyons are out there, they could point to regions of the universe where time's arrow doesn't just bend, it flips entirely. Picture a pocket of space where entropy decreases, where shattered glass reassembles and smoke funnels back into chimneys. In such a place, tachyons might be the native particles, as natural as electrons are here. Some theories even suggest that tachyons could be the key to understanding dark energy, their exotic properties driving the accelerated expansion of the universe in ways we can't yet fathom. The real puzzle isn't just whether tachyons exist, it's what their existence would mean for our understanding of time. If particles can move backward through time, does that imply time itself is more fluid than we thought? Could entire regions of the cosmos be ticking in reverse, their histories unfolding from future to past? Or are tachyons merely mathematical phantoms, mirages in the equations that vanish under closer scrutiny? For now, the answers remain hidden, waiting for a breakthrough that could rewrite physics, or relegate tachyons to the realm of fascinating but unrealized possibilities. Until then, they linger at the edge of science, a reminder that the universe's rulebook might still have pages we haven't turned. What if everything you remember, every sunrise, every conversation, even the act of reading these words wasn't real, but a fleeting hallucination of a brain that spontaneously formed in the void? This is the chilling premise of the Boltzmann brain, a thought experiment that takes randomness to its logical extreme. Named after physicist Ludwig Boltzmann, who grappled with entropy and probability in the 19th century, the idea goes like this: given enough time, even the most improbable events become inevitable. In an infinite, chaotic universe, particles could randomly arrange themselves into a fully formed, self-aware brain complete with fabricated memories of a past that never existed. Picture this brain floating in the darkness, convinced it's lived a full life, only to dissolve back into chaos moments later. It's a cosmic glitch, a hiccup in the void's monotony, but one that forces us to confront a terrifying question: how do we know we're not Boltzmann brains ourselves? If randomness can conjure consciousness, then the flow of time we take for granted might be nothing more than an elaborate fiction. The seconds ticking by, the aging of stars, even the Big Bang itself could be figments of a transient mind, destined to vanish as suddenly as it appeared. The paradox deepens when you consider entropy, the universe's tendency toward disorder. Boltzmann's work showed that low entropy states like a fully formed brain are statistically unlikely but not impossible. In a universe lasting trillions of years, these fluctuations become inevitable. Some physicists argue that it's far more probable for a single brain to pop into existence than for an entire ordered universe like ours to arise by chance. So why do we see galaxies and planets instead of isolated minds drifting in the dark? One answer lies in the nature of memory and perception. A Boltzmann brain wouldn't just think it had a history, it would feel it, with every neuron firing exactly as if it had experienced decades of life. Your childhood home, the smell of rain, the weight of time's passage, all could be illusions woven by randomness. This isn't just solipsism, it's a radical challenge to empiricism itself. If we can't trust our own memories, how can we trust science, history, or even the concept of time? Critics counter that the Boltzmann brain scenario is a reductio ad absurdum, a logical extreme that highlights flaws in our assumptions. If the universe is old enough for such fluctuations to occur, why haven't we observed other, simpler random structures? Why no floating chairs or halfway formed galaxies? Some theorists propose that the very laws of physics might prevent Boltzmann brains, with quantum decoherence or entropy gradients acting as cosmic safeguards. Others suggest that consciousness requires more than just neural patterns. It might need an embedding in a stable, causal universe, something a flickering brain could never provide. Yet the thought experiment lingers, forcing us to grapple with time's fragile foundation. If reality can be simulated by chance, then time's arrow might not be a fundamental feature of the universe, but a local quirk, or worse, a mirage. The Boltzmann brain doesn't just threaten our sense of self, it undermines the very framework we use to understand existence. And in a strange twist, the only way to dismiss it is to rely on the very memories and observations it calls into question. So where does that leave us? Perhaps the answer isn't in defiance, but in perspective. The Boltzmann brain reminds us that time and consciousness are mysteries wrapped in probabilities, and that certainty itself might be the most fragile illusion of all. Whether we're stable beings in a real universe or fleeting flashes in the dark, the questions we ask and the awe they inspire are what make us feel alive, however briefly. Gravitational waves are more than just cosmic tremors, they're whispers from the universe's most violent events, carrying secrets about the very fabric of reality. When two black holes spiral into each other or neutron stars collide, they don't just release energy, they send ripples through space-time itself, warping the distances between stars and planets like a stone disturbing a pond. But these ripples might hold clues to something even more profound, the possibility that time itself flows differently in different parts of the cosmos. Think of space-time as a vast, stretchy sheet. A gravitational wave passing through it doesn't just bend space, it stretches and compresses time too. Imagine two synchronized clocks placed miles apart. As a gravitational wave rolls by, one clock might momentarily tick faster than the other, not because of any mechanical flaw, but because time itself is being distorted. These fluctuations are vanishingly small, a fraction of a second, but they're real. And if we can measure them, we might catch glimpses of time's hidden variability across the universe. This is where LIGO, the Laser Interferometer Gravitational Wave Observatory, becomes our time detective. By bouncing lasers down miles-long tunnels, LIGO detects the infinitesimal stretching and squeezing of spacetime caused by passing gravitational waves. Each wave is a fingerprint of the cataclysm that created it, encoding details about the objects involved, their masses, spins, even how they distorted spacetime in their final moments. But buried in that data could be something even more startling, evidence that time doesn't flow uniformly everywhere. Consider a gravitational wave generated near a supermassive black hole, where gravity is so intense that time slows to a crawl. As the wave travels across the cosmos, it might carry an imprint of that time-warped environment, like a tape recording played at the wrong speed. By analyzing the wave's shape and frequency, scientists could potentially reconstruct the time signature of its origin, revealing whether clocks tick faster or slower in distant galaxies. The implications are staggering. If gravitational waves can testify to time's variability, they might confirm that the universe isn't just a single timeline but a patchwork of temporal zones, each ticking to its own rhythm. Civilizations near black holes or in regions thick with dark matter could experience centuries while the rest of the universe races ahead. Even stranger, some theories suggest that gravitational waves from the early universe, when spacetime was still settling into its current form, might carry echoes of a time before time was fully set, like fossilized ripples from an era when the rules were still being written. Yet the hunt for these clues is just beginning. Future observatories like the space-based LISA mission will listen for lower-frequency gravitational waves, ones that might have traveled for billions of years, their waveforms subtly altered by the shifting flow of time across cosmic history. Other projects aim to combine gravitational wave data with observations of pulsars, neutron stars that spin with near-perfect regularity, acting as celestial metronomes. If gravitational waves passing through pulsar-rich regions alter their ticking in predictable ways, we might build a map of time's uneven terrain across the galaxy. Gravitational waves don't just reveal where spacetime has been warped, they hint at how time itself might be woven into the universe's deepest mysteries. From black holes to the Big Bang, these ripples are more than cosmic messengers. They could be the key to understanding whether time is a universal constant or just another thread in spacetime's ever-shifting tapestry. Black holes aren't just cosmic vacuum cleaners, they're shredders of reality itself. When matter crosses the event horizon, it's not just crushed into oblivion. According to Stephen Hawking's groundbreaking work, it's slowly evaporated back into the universe as a faint glow of radiation. But here's the catch: Hawking radiation carries no information about what fell in. No fingerprints of atoms, no traces of stars, just thermal noise like static on a radio. This creates a paradox that shakes physics to its core. Quantum mechanics insists information can never be destroyed, only scrambled. Yet black holes, if Hawking was right, seem to erase it permanently. So where does the truth lie? The answer might rewrite our understanding of time itself. Picture tossing a book into a fire. The pages burn, but the information isn't truly gone. It's transformed into heat, smoke, and ash, all carrying echoes of the original text. In theory, with perfect knowledge, you could reverse the process and reconstruct the book. But a black hole, it's like a fire that burns the book and then evaporates the smoke into pure, featureless warmth. No reconstruction, no echoes, just silence. This isn't just a problem for physicists, it's a crisis for reality's very rules. If information can vanish without a trace, the universe becomes unpredictable, unanchored. Cause and effect fray at the edges, and time's arrow, the steady march from past to future, loses its meaning. The stakes couldn't be higher. If black holes truly erase information, then quantum mechanics, the most successful theory in history, is fundamentally flawed. But Hawking himself later backtracked, suggesting information might escape after all, just in forms we can't yet decipher. This sparked a firestorm of debate. Some theorists propose that black holes don't destroy information but encode it in their event horizons, like a cosmic hard drive. As particles exit as Hawking radiation, they'd carry away scrambled bits of that data, preserving the universe's ledger in ways we're only beginning to understand. Others argue for more radical solutions, like black holes birthing new universes where the information reemerges, or holographic principles where three-dimensional reality is a projection of two-dimensional data stored on the event horizon. But the most tantalizing clue might lie in time's own fabric. In quantum mechanics, time is reversible. Equations work just as well backward as forward. Yet black holes, with their one-way event horizons, seem to enforce irreversibility. This tension could hint at a deeper truth, that time's flow isn't just a backdrop but an active player in the paradox. Perhaps information isn't lost but trapped in time loops near the singularity, or maybe the very concept of before and after breaks down at the quantum level, making the paradox itself an illusion. The mystery remains unsolved, but one thing's clear: black holes aren't just testing gravity or quantum theory, they're probing the nature of reality itself. And if we ever crack the information paradox, we might not just save quantum mechanics, we could uncover time's deepest secrets, hidden in the darkness where space and meaning collapse. The Alcubierre drive sounds like pure science fiction, a theoretical engine that could zip across the galaxy by bending spacetime itself. But the physics behind it is shockingly real, rooted in Einstein's equations of general relativity. Imagine a spacecraft nestled inside a bubble of distorted spacetime, where the fabric of the universe ahead contracts like a scrunched-up rug, while space behind expands like a stretched rubber band. The ship itself wouldn't move through space. Instead, space would move around it, carrying it forward faster than light without breaking any universal speed limits, at least not locally. It's like surfing a cosmic wave where the water is spacetime itself. But here's the twist: while the Alcubierre drive sidesteps the light-speed barrier, it doesn't escape time's grip. Passengers inside the bubble might experience time entirely differently than those outside. Picture a journey to a star 10 light-years away. To observers on Earth, the trip might appear to take 15 years. Yet inside the warp bubble, time could crawl or race depending on how spacetime is manipulated. If the bubble's geometry creates extreme time dilation, the crew might age only weeks while decades pass back home. The opposite could also happen. Time inside might speed up, turning a short trip into a centuries-long exile for the travelers. The real puzzle lies in causality. If an Alcubierre-driven ship arrives at its destination before light could get there, even from Earth's perspective, it creates paradoxes. Events could unfold out of sequence, breaking the chain of cause and effect. A message sent via warp drive might reach its destination before it was even transmitted, a scenario that makes physicists shudder. Some theories suggest such violations might be prevented by quantum effects or hidden physics that slap a "no trespassing" sign on certain warp configurations. Others argue that the drive's energy requirements, traditionally thought to need exotic matter with negative energy, are so absurdly high that nature itself might forbid it. Yet the dream persists, fueled by tantalizing hints that warp effects might not be pure fantasy. Recent refinements to the math suggest ways to reduce the energy needed, perhaps even to plausible levels. Experiments with metamaterials, engineered structures that bend light in weird ways, have created tiny, lab-scale analogs of spacetime curvature, offering glimpses of how warp physics might play out. And if black holes can warp time, why not a machine built to do it on demand? The Alcubierre drive forces us to confront a profound truth: faster than light travel isn't just about speed. It's about hacking the universe's operating system, rewriting the rules of time and distance. And if we ever crack the code, the galaxy wouldn't just open up to us, it might rearrange itself in ways we can't yet imagine. From black holes to multiverses, we've journeyed through theories where time is anything but constant, where seconds stretch like taffy in one corner of the cosmos and vanish in a blink in another. Imagine standing at the edge of a supermassive black hole, watching clocks on Earth tick frantically while yours barely moves. Or picture a universe where time loops back on itself, trapping civilizations in endless cycles of birth and collapse. These aren't just thought experiments, they're real possibilities etched into the equations of relativity and quantum mechanics, waiting for us to uncover their secrets. What's astonishing isn't just that time might flow differently elsewhere, it's that we've even begun to unravel these mysteries at all. Think about it, with nothing but math, ingenuity, and a relentless curiosity, we've peered into the heart of black holes, decoded the whispers of gravitational waves, and dared to ask whether time itself could be an illusion. Every breakthrough, from Einstein's revelations to the eerie discoveries of quantum entanglement, has chipped away at the illusion that time is a universal metronome. Instead, it's starting to look like a cosmic symphony, with each region of space playing its own tempo. Yet for all we've learned, the biggest questions remain wide open. Is time fundamental, or does it emerge from something deeper? Could there be places where it runs backward or stops altogether? And if we ever meet civilizations from other corners of the universe, would we even recognize their concept of now? The beauty of these puzzles is that they push science to its limits, forcing us to rethink not just the universe, but our place within it. Every anomaly, like the Pioneer probe's strange deceleration or the eerie synchrony of entangled particles, hints at layers of reality we've yet to perceive. So where does this leave us? In a universe where time is fluid, the next frontier might not be a place, but a perspective. The tools we'll need to explore it: quantum computers, space-based observatories, even theories we haven't dreamed up yet, could unlock truths that make today's debates look quaint. One day, we might find clocks that tick in fractions of a second here but count epochs elsewhere, or stumble upon relics from a time before time had meaning. Until then, the mystery itself is the compass, guiding us toward discoveries that could rewrite not just physics, but the story of existence. The adventure is just beginning. What cosmic secrets do you think are hiding in time's wrinkles? Drop your wildest theories in the comments. And if you've enjoyed this dive into the unknown, hit subscribe, because the universe has far more surprises in store, and we're just getting started.